So we can take the globals, we can write them to each thread stack, that way they're protected, and then when I need to do a context switch, I then write the values back into the global space. That is one mechanism. But it's not a perfect mechanism. So other IPC mechanisms are going to come into play instead. Okay? This is an excellent example of doing a shared resource, like a common variable. Okay? Where you have, in this case here, it could be two processes, but it also could be two threads. Okay? Get char, or get c, okay, is a system call that we're going to play with along with put char or put c, using two variables, char in, char out. Okay, so the idea being is that if I have one process running, right, it calls get char, stores it to char in, and at some point I write char in to char out, and then I do the put char to char out. If it was a local copy, no problem, right? If it was not a local copy, and I had these two processes running, I might have this process running, then it did a context switch. Then this process got to run. The value of char out is going to change here, and then when this process goes to run again, it's going to have a different value of char out than what it had in its own space, if it was truly global. See that? Okay. So, to manage that, we are going to introduce this notion of critical sections. I shouldn't say notion, it's more than a notion. Whole collection of algorithms and tools for critical sections. Okay? To implement and talk about critical sections, we're going to need to understand these three terms very, very carefully. Mutual exclusion. Mutual exclusion says that one process, and only one process, may be in its critical section at any given time. That's mutual exclusion. Progress. Progress says that if any process is waiting for the critical section, only the process that's in its critical section may decide who gets to run next. Put another way, well, there's put another way there. Okay. Thing to point out is that depending upon how we implement progress, we can create deadlock if we're not careful. We have a whole chapter on deadlocks, so I don't want to go into that just now. Just understand that deadlocks are bad, okay? And this is one way we can get into a deadlock situation. So to prevent that, we're just going to say progress says that in order, well, it's not in order. We have multiple processes waiting for the critical section. Only the process that's in its critical section may determine which process gets it next. Okay? By the way, there's a lot of talk about critical sections. So code that is not in its critical section is said to be in its remainder section. And the bulk of your code is in the remainder section. It has a name. So if we say, what happens if it's not in its critical section? Oh yeah, it's in its remainder section. And we don't care. Process in their remainder section, they can have a great time, do whatever they want. It's when they go into a critical section that we need to be concerned with these definitions in our algorithms for managing them. Another thing to be concerned about too is that a lot of times your authors, including your author, when they talk about critical sections, they don't make it very clear that you can have multiple critical sections. You can and will typically have multiple critical sections. You're going to have a critical section for every shared resource your process uses. Every shared resource your process is going to use is going to have a critical section. So these are talking about a critical section. Okay? So that's mutual exclusion, progress. Bounded waiting says that there will be a limit on the times that a process will wait for its critical section before another process may return to its critical section. In other words, it's got to be fair. I can't have one process saying, I just had the critical section, I'm going to go grab it again. And I've got other processes that want to get into their critical section too. No. I'm going to limit the number of times a process can return to its critical section if I have other processes waiting. Other processes need to get a turn. Everybody's going to play nicely in this sandbox, okay? So bounded waiting, that's what we're talking about here. So, that's the big three. Excuse me. Let's take a look at how this comes into play. You have process A, and process B, and time. Process A comes in over here at this point, says, I want my critical section. Fine, it gets its critical section because nobody else is in that critical section right now. So we have no issues. No one's using that critical section. Great. Process A gets there first, it gets to use it. So off it goes, it's in its critical section. Sometime later at T2, process B says, oh, I need that critical section. Well, guess what? Right now, there is already a process in its critical section. So to support mutual exclusion, I'm going to block process B. Mutual exclusion says only one process may be in this critical section at any given time, right? Yeah, you knew that. Okay. So it's going to wait, and then process A completes its work with the critical section. Recognizing that there's now a line of one, maybe more, processes waiting for its critical section, and recognizing that it must implement progress, it will look around and say, oh, process B requested it, nobody else did, so I will select process B to go into its critical section, and it releases it to process B, and off it goes into its remainder section. Process B does its work, it releases its critical section, it looks around, nobody else is waiting for it, so it simply releases it and goes off and does its thing. Right? Makes sense? That's an easy example. Okay. So solving it, recognizing that we have to implement all three of these with multiple processes, with multiple needs for their critical section, including the numbers of times they use it, how long they hold the critical section, all those different things. There's a number of solutions that have been proposed and have been implemented in different operating systems for managing our mutual exclusion problem. So this impressive little list here should tell you a couple things. One, we haven't solved it perfectly. Two, it's ripe for research. And three, we're going to spend some time looking at some of these algorithms, right? Okay, a couple of these are really simple and straightforward. I'll leave the first two as readings to you for the weekend. Likewise, strict alternation is just brain dead simple and also stupid. So we're not going to spend much time looking at it. It simply says, I had it, it's your turn. I had it, it's your turn. No, it doesn't work. However, Peterson's solution is a classic that we need to look at and is actually implemented in some operating systems. We're also going to be looking at these mechanisms for implementing what we call the producer-consumer problem to solve the critical section problem with. Many of you might have heard of the classic dining philosophers problem. We're going to look at that, as well as the readers-writers problem. Okay? These are different techniques we have. Some work better than others, but they're all worth taking a look at because, as I just mentioned, none of them are perfect. Okay, strict alternation, like I said, is brain dead. That's it. Peterson's, however, is worth taking a look at. There's the point where I was going to say, you need to stop for tonight. We'll pick up on this one. You want to do your readings on this. It's going to take longer than we have time to start diving into the rest of these algorithms. And we'll pick it up again on Wednesday, because Monday's a holiday.